goodie. Let's say we want to integrate x e to the x dx. From our previous class, we know to use integration by parts, and we will get the answer x e to the x minus e to the x plus c. What about if we integrate x squared e to the x dx? Well, we'll have to use integration by parts twice to get to our answer, which works out to be e to the x into x squared minus 2x plus 2 plus c. What about if we wanted to integrate x to the 5 e to the x dx? It simply means that we will have to use integration by parts 5 times. And similarly, if you want to integrate a higher power of higher power, let's say x to the n e to the x dx, alright, we'll have to use integration by parts n times. Also, let's say we have to integrate, let's say, sine x. Well, we know that the integral of sine x dx, well, is equal to negative cos x plus c. What about if we integrate sine squared x now? Well, definitely we'll have to use the double angle formula of cos 2x. Make sine x the subject of the formula and integrate. What about sine cube x? Again, you'll have to use the triple angle formula to work out this. And let's go down. Let's go to another higher power of n, of sine x, sorry. What would we do? So, what we would like to do today is to somewhat derive a formula for higher powers of integrals and try to simplify them. And the method by which we are going to do that today is by using what we call the reduction formula. So let's look at our first example. Let's say we have the integral between 0 and 1 of x to the n e to the x dx. Well, from previous experience, how we can integrate this is by using integration by parts. But first, let us equate this to I subscript n. And just to let you know, for future reference, is that the subscript and the power, they will correspond to one another. So what we're going to use is integration by parts here to work out this question. So we're going to let v equal to x to the n. So dv dx is going to be n x to the n minus 1. And our du dx, which is equal to, in this case, e to the x, our u is going to be equal to e to the x. So in is going to be equal to uv, which is x to the n e to the x, evaluated between 0 and 1, minus now the integral of nx to the n minus 1 multiplied by e to the x dx. So let's evaluate. So this is 1 to the power of n e to the 1 minus 0 by e to the power of 0 minus now n times integral of x to the n minus 1 e to the x dx. When we simplify this bracket, we're going to get e minus n, and let's put in our limits here. Don't forget to put in your limits. Now, if you look at what we have here and what we started off with, we will see that x to the n minus 1 e to the x is very similar to x to the n e to the x. So remember, as we started this example, I did say that the subscript in in should always correspond to the power in the integral. So therefore this becomes in minus 1. So this here is our reduction, what we call the reduction formula for this particular integral. And let's see how we can put this to use. Let's say we want to find the value of I4. Now I4, it's really the integral between 0 and 1 of x to the 4th e to the x dx. So using our formula here, we will get that in, or I4, I'm going to substitute n is 4, is equal to e minus 4 times I3. And now we know what we could now find what I3 is. I3 is equal to e minus 3 times I2. And in a similar manner, if we substitute n is equal to 2, we're going to get I2 is equal to e minus 2 times I1. And I1 could be equal to e minus I0. So what we have done is to reduce the higher order in our higher power integral into something that we can simplify, I0. So I0 is equal to the integral between 0 and 1 of x to the 0 e to the x dx. And that is equal to the integral of e to the x dx between 0 and 1. And this is going to be equal to, well, it's e to the 1 minus 1. So that is I0. So what we're going to do now is to substitute for I0 into the formula for I1. So I1 is equal to e minus 1, which will give us 1. I2 now is e minus 2 times I1, which is e minus 2. I3 is equal to e minus 3 times I2, which is e minus 2. So that will give us 6 minus 2e. And I4 is equal to e minus 4 times I3, which is 6 minus 2e. And that will give us 9e minus 24. So therefore, the integral of x to the power 4 e to the x dx evaluated between 0 and 1 is equal to 9e minus 24. So if you wish, you could try using integration by parts 4 times and see if you come up with the same answer. But as you will realize is that using the reduction formula, the integral becomes a lot easier, especially when you have higher powers of integrals to deal with. Let's look at another example. And this example is the integral of sine x to the power of n evaluated between 0 and pi over 2. So we are going to split up sine x to the power of n into sine x by sine x to the n minus 1 dx. So we're going to let v equal to sine n minus 1x. So our dv, and we're going to differentiate this using the chain rule, and this would be n minus 1 times sine, we reduce the power by 1, so we get m minus 2x. And don't forget to multiply by the differential of sine x, which is cos x. Over du dx, that is equal to sine x, and the integral of sine x is equal to negative cos of x. So therefore now in is equal to uv, so it's sine n minus 1x by cos x evaluated between 0 and pi on 2 minus the integral between 0 and pi on 2 minus cos x by n minus 1 sine n minus 2x cos x dx, which equates to, and we know that sine of pi on 2 is 0. No, sorry, sine of pi on 2 is 1, but cos of pi on 2 is 0, and the sine of 0 is 0. So this evaluation goes to 0. Negative by negative is a positive. So this is n minus 1, the integral between 0 and pi on 2 of sine n minus 2x cos squared x dx. Which reduces to now n minus 1, and we know that cos squared x, it's 1 minus sine squared x. So we're going to use that substitution, and let's simplify. This is sine n minus 2 when we expand the brackets minus sine nx dx, which works out to be n minus 1, the integral between 0 and pi over 2 of sine n minus 2x dx minus the n minus 1 times the integral between 0 and pi over 2 sine nx dx. And if we recognize from earlier that this integral here, or the integral of sine nx, sine x to the power of n minus 2 is really in minus 2 minus n minus 1 now, and the integral of sine x to the power of n evaluated between 0 and pi over 2 is in. So let's take the in across, and we get n minus 1 in plus in is equal to n minus 1 in minus 2. So this now simplifies to n times in is equal to n minus 1 in minus 2. So therefore in is equal to n minus 1 on n in minus 2. And this integral is valid for n greater than or equal to 2. So the integral of sine nx, or sine x to the power of n, simplifies to a very simple formula, or again what we call the reduction formula.